In a thunderstorm, charge is separated through a complicated mechanism that is ultimately powered by the sun. A simplified model of the charge in a thundercloud represents the positive charge accumulated at the top and the negative charge at the bottom as a pair of point charges. What is the electric potential energy of the pair of point charges, assuming that U equals 0 when the two charges are infinitely far apart? Explain the sign of the potential energy, given the fact that positive work must be done by external forces in the thundercloud to separate the charges. Well, let's begin this example with a sketch of our thundercloud. So we have a thundercloud. Yeah, not as good as the picture that I have here. And what is happening in this thundercloud is a separation of charge. Positive charge is accumulating at the top of the thundercloud. I'll call that charge Q1. And negative charge is accumulating at the bottom of the cloud. Let's call this Q2, where Q1 is 50 coulombs in magnitude, and Q2 is minus 20 coulombs. Now, how thunderclouds work is typically a thundercloud will end up having a net charge. Now, in this situation, there is a net charge, a net positive charge at the top of the thundercloud. So if the charge separation was great enough and the difference in charge was great enough, you would often expect there to be maybe some discharge between those two portions of the cloud. However, if the cloud gets pretty close to the surface, what'll happen is, at least in this example, the negative charge at the bottom of the cloud will induce positive charge in the ground. And if there is enough difference in charge, then you will have a discharge. Lightning will strike. Our goal in this problem, however, is just to determine the electric potential energy between the charges in the cloud, so between Q1 and Q2. Potential energy is shared energy. Whenever we talked about gravitational potential energy, two masses were always involved, believe it or not. For example, the gravitational potential energy of an apple falling to Earth. Well, that's an energy shared between apple and Earth. In this case, it's the electric potential energy between two unequal charges, Q1 and Q2. So let's write down the formula we have for the electric potential energy due to a pair of point charges. The electric potential energy due to a pair of point charges is based off of their separation distance, and it's given as the Coulomb constant times the product of the charges divided by the distance between them. But this definition only applies if we have the condition that the electric potential energy infinitely far away is equal to 0. Potential energy is really defined as a change of potential energy between 2 points given as minus the work done by a conservative force in displacing an object between 2 points. So what does that have to do with how we define electric potential? Because it might be contradictory, or you might say, well, Mel, you define that the electric potential energy due to a pair of point charges is equal to a particular value based off of the separation distance. Well, this convention is true if we say the potential energy at a point very far away is defined to be zero. If you remember when we derived the potential energy due to a pair of point charges, we had the potential energy at a point, I'll call point B, R of B, minus the potential energy at point A is equal to K Q1 Q2 over R of A. Sorry, that should be R at B minus K Q1 Q2 over R at A. Well, if we're saying that our final position is infinitely far away, well, for point B, that ends up being a very, very large number in the denominator. With this said, we know that a finite number divided by an infinitely large number, that term is going to go to zero. So we now have the potential energy at infinity minus the potential energy at some finite point in space. I'll just now relabel R at A, I'll just relabel it to R, is equal to 0 minus K Q1 Q2 over R. And here is where we are saying the potential energy at infinity is defined to be 0, which means with that convention, we could hold that the potential energy between a pair of charges separated by a finite distance is equal to this expression right here. It is equal to the Coulomb constant times the product of the charges divided by the distance between the charges. And as a reminder, this once again is saying that we are defining the electric potential energy when they're infinitely far away to be 0. This is why this problem said, assuming that U equals 0 when the two charges are infinitely far apart. That allows us to use this formula right here instead of the difference, instead of the change of potential energy. We can now say this is the potential energy at a point because our reference point is a point infinitely far away. Now we are able to write down the solution to this problem. The electric potential energy between these pair of charges is equal to K Q1 Q2 over R. The Coulomb constant is 8.99 times 10 to the 9th newtons meters squared over Coulomb squared. Charge 1 is 50 coulombs of charge. Charge 2 is minus 20 coulombs of charge. And this is divided by the separation distance of 8 kilometers. So 8 times 10 to the 3rd meters. Doing a unit check in line, we have a Coulomb squared in the numerator, cancels with a Coulomb squared in the denominator. We have a meter in the denominator, cancels with one of the meters in the numerator. And we have final units of being a Newton meter. A Newton meter is a joule. Plugging this into my calculator, I get that there is minus 1 times 10 to the 9th joules of electric potential energy between the charges in our thundercloud. Minus 1 billion joules of energy. That's a lot of energy.